Hello and welcome back. This will cover 5.6. So we're looking now at some more advanced logarithmic and exponential equations and how we can solve them. So we've spent a couple videos defining exponential functions and their properties and their inverse, the logarithmic functions and their properties. And now we're going to combine it all together to solve various equations utilizing those properties in order to find some unknown. So let's jump right into it. So we have a recap of some important properties. This first one we've seen a bunch. This is that translation between logarithmic and exponential form. And then this statement is saying basically we can take a logarithm of both sides, or if we have a logarithm with the same base on both sides, we can just equate what's inside. That's kind of equivalent to a similar statement we made about exponentials too. So let's keep this in mind as we look at these examples. Let's just jump into the first one. We're given 2 times the log base 5 of x equals log base 5 of 9. So what can we do? We're trying to solve this x. Well, we have a log base 5 on both sides. First, I'd want to deal with this number in front. Remember that if we have a number in front of a logarithm, we have like a times log of b, we can move it up inside the logarithm as an exponent. So b to the power a. And vice versa. This can go both ways. We can either move it outside or move it inside. So let's use that property. We can write this as log base 5 of x squared equals log base 5 of 9. Now we have log base 5 on both sides, so if log base 5 of blah equals log base 5 of other blah, well, the two blahs must be equal to each other. I'm just using that as a general placeholder. So I can say x squared must equal 9. And then I would take the square root of both sides. So I would say x equals plus or minus 3. And it's tempting to stop there, but let's remember the domain of the logarithmic function. What's the domain? It was all values greater than 0. So it can't be equal to 0, and it cannot be negative. And it doesn't just mean if I have a negative x, because I still could plug a negative x inside of a log, and maybe it gets added to some number that makes it positive in the end. So that doesn't necessarily mean we should automatically throw it out. We want to look in context at the logarithms we have. But however, in this case, we do just have x. So if we were to plug in that negative 3, we would be outside the domain of the logarithmic function. So we got to say x can't equal that negative 3. So we'll just take the positive as the result. X will just equal positive 3. But here we're using that property. If we can set it up so we have a logarithm with the same base on both sides, you can just equate what's inside of them. Let's see another example. Here we have log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. What can we do? Well, let's recall that if we have an addition of two logarithms with the same base, we can combine it into a multiplication. If we have log of a plus log of b, and I'm just writing log, we can imply base 10, basically just saying that the base is the same. This is equal to log of a times b. We can bring them together. That will at least condense things for us. We can make this log base 5 of x plus 6 times x plus 2, okay, equal to 1. But we really want this to be just the log base 5 of something on both sides. Well, 1, how did we get a 1 with a logarithm? Remember if we had, say, like log base a, where that base was also inside, these canceled out and we just got 1 as the result. So let's just re-express that 1 as log base 5 of 5. Hopefully that feels okay. We can turn a 1 into any logarithm using that property. So now we're in that condition where we have log base 5 of something equals log base 5 of something else. We can just say whatever's inside is equal to each other. X plus 6 times x plus 2 should be equal to 5. Cool. Now let's just solve for x. We have looks like an old school quadratic problem. So let's multiply this out. We need to get this all equal to 0. So I'll FOIL it out. That would be what? X squared plus 2x plus 6x plus 12 equals 5. So x squared plus 8x, and I'll subtract the 5 over, so 12 minus 5 is 7, equals 0. Now factors of 7 that add up to 8, well that would be 7 and 1, so x plus 7 times x plus 1 equals 0. Let's set them both separately equal to 0 and solve. You should get that x equals negative 7 and x equals negative 1. Hopefully solving the quadratic stuff, you're comfortable with that at this point. If not, it might be worth returning back to some of those basics. We have 2 negative answers. That's not necessarily bad, but let's check our original statement and see if we plug either of these in, would we break the domain? Would we get some negative value inside? Well, I see with the negative 7, if I plug that into this first one, negative 7 plus 6 would be negative 1. So can't use that one. Even if it's only one of the logarithms, I guess it would still happen here too, but it needs to only break the domain of one of them from the question. So we can't have negative 7. What about negative 1? If we plug it in here, negative 1 plus 6 is positive 5, so that's okay. If we plug it in here, negative 2 plus 1 is 1, so that's okay. So we can take this negative 1 as our only solution. So sometimes we have to throw out some because of the domain of the logarithm. All right, let's look at another example. So now we have natural log of x equals natural log of x plus 6 minus natural log of x minus 4. So I see the natural logs. I see a subtraction of 2 natural logarithms. So let's combine those together into a division. Recall that property. If we have natural log of a division, it can be split up into a subtraction or vice versa. If we have a subtraction of 2 logarithms with the same base, it can be combined together into a single logarithm with the original arguments divided. So let's rewrite this as the natural log of x equals the natural log of x plus 6 over x minus 4. Cool, now we have log with the same base on both sides, so let's just equate what is inside of them. I can say x equals x plus 6 over x minus 4. I'm making little mental notes like x probably shouldn't equal positive 4. You would divide by 0. I'm going to just write that on the side, just in case we get that as one of our solutions. and then you could say, you can already like start to think about what's going to break the domain of these. It's good to consider. So let's keep working on solving this equation. How about we multiply that denominator over to the other side? So I'll get x times x minus 4 equals x plus 6. And then we can distribute that x to both terms. So that will give me x squared minus 4x equals x plus 6. Let's get everything over to one side. I'll subtract the x over, so x squared. This will become minus 5x, and then I'll subtract the 6 over. So x squared minus 5x minus 6 equals 0. Okay, we can factor and solve. This is supposed to have an x here. So factors of negative 6 that add up to negative 5. Two things that multiply to negative 6 that when I add them I get negative 5. What should be positive and what should be negative? I want the result to be negative, so I think I'll take negative 6 and positive 1. Yeah, that should work out. So this will factor into x minus 6 times x plus 1 equals 0. Then let's solve each one separately, set them both separately equal to 0 and solve. So we would get x equals positive 6 or x equals negative 1. But let's check. If we use positive 6, 6 plus 6 is positive. That's good. All I care about is if it's positive or negative. 6 minus 4 is still positive, so that looks good. For the negative 1 plus 6 is positive 5. But here, notice negative 1 minus 4 would be negative 5. So can't have the negative 1. So we'll just take the positive 6. So keep an eye out for that. If you're trying to work on the homework questions and you feel like you have the right answer, but it's rejecting it, maybe it's because it is outside of the domain of the natural log or in any particular logarithm. All right, let's look at it from the exponential side. So similar properties. If we have the same base on both sides, we can just equate the exponents. So let's use that fact. For a, we have 2 raised to the power x equals 5. What can we do? I think here we might have to end up doing an approximation. I think we saw something like this last time. But we still want to solve for x and get at least some kind of exact statement that maybe we can plug into a calculator and solve. So we could turn this into exponential form, or you can just use whatever logarithm you like on both sides. I like the natural logarithm. So I can take the natural log of 2 raised to the power x equals the natural log of 5. I can use that exponent rule and bring the x out in front. So I can say x times the natural log of 2 equals natural log of 5. So at this point, these are just some numbers. It looks complicated, but it's just ultimately 2 values. So I want to solve for x, so I'll just divide that ln of 2 over. So you could leave this as an exact answer if it did ask for something exact. Or if you plug it into a calculator, you would get approximately 2.322. So B is just very similar. We have 8 times 3 to the power x equals 5. Let's first just isolate this 3 to the power x, the term that has our unknown. So I'll divide the 8 over. So 3 to the power x would equal 5 over 8. And then I'm just going to take the natural log of both sides. We could convert it into a logarithm with a base of 3, but I'll assume maybe we have a calculator that doesn't let us input whatever base we want. So I'll use the natural log because it'll definitely have that. All right, then we can bring the x out in front. So x times ln of 3 equals ln of 5 over 8. And then let's just divide that logarithm over. Ln of 5 over 8 over 3. That's something, oh, not 3, but the natural log of 3. So that's something that we could plug in if we needed to. Okay, let's look at another example. We have 5 to the power of x minus 2 equals 3 to the power of 3x plus 2. If these were the same base, if they were both 5 or both 3, we could just equate the exponents, or maybe we could turn one into the other, like we've done before, but it'd be hard to turn the 3 into a 5 somehow using some power. So let's just use this idea. I'm just going to take the natural log of both sides. I can say ln of 5 to the power x minus 2 equals ln of 3 to the power 3x plus 2. And then we can apply that exponent rule to both of these. I can bring the x plus 2 out in front here. So x plus 2 times now just ln of 5 equals 3x plus 2 times just ln of 3. So you can see sort of the power of logarithms. It's a way of like accessing an exponent if your unknown is within the exponent of something. It's a way of getting it out, bringing it down. But what can we do? How can we solve this? Well, imagine that this is just some number, like a and b. It's just some other number. What would you do? You would distribute that through and then try to clean everything up and solve for x. So let's just do that. Let's distribute it to both terms. So this would give me x times ln of 5 plus 2 times ln of 5. And on the right side, we'll distribute as well. So this would be, how should we write this? Like, we'll write it as 3x times ln of 3 plus 2 times ln of 3. It looks messy, but keep in mind ln of 5 and ln of 3 is just a number, just some number. So what would you do normally in solving an equation? We would try to collect all of your x's on one side and get everything else over to the other side. So I'm going to move all the terms that have an x to one side. I'm going to move this 3x term over here. And this term doesn't have an x, so I'm going to move it to the other side. So I'll still have this x times ln of 5 over here. This will be subtracted over, so it will appear as negative 3x times ln of 3. And then I'm moving this term to the other side. So on the right side, we will have the 2 times ln of 3 now minus 2 times ln of 5. Still looks pretty messy, but notice on the left side, both terms now have an x, so we can factor that x out of that whole expression. Let's just bring it out in front. So x times ln of 5 minus, and we took the x out, so there'll just be 3 times ln of 3. equals everything on the right side. Now, we have our x factored out, so let's just divide this whole thing. Again, this is just going to be some number. There's no unknowns in there. We could type that in and get some decimal, but I want to try to stay as exact as possible. So let's just divide that whole term in parentheses. So I can say x, notice it's going to be solved for x now, equals everything that was on the right side, 2 ln of 3 minus 2 ln of 5, divided by that whole term, ln of 5 minus 3 ln of 3. And honestly, I'm just going to call that our solution. We can say this is our exact solution. We could plug all that into a calculator and get some decimal. We could also express this in many different variations using properties of logarithms. Like we could factor this 2 out of the numerator, and then we would have a subtraction of logarithms. We could express that as a division, like 5 over 3 inside. Um, but I'll just leave it here. There's a few different ways we could ultimately express the answer. But here we have it solved for x. X is equal to whatever this whole right side becomes after we evaluate it. So looks kind of messy, maybe a little bit less satisfying, but since this is in the examples, I can assume there'll be some homework questions in this style. So just try to collect all of your terms that have your unknown on one side of the equation, then factor out your unknown, and then you can just divide everything else over. So a little trick. All right, we got just one more example here. We have 4 to the power x minus 2 to the power x minus 12 equals 0. What can we do here? So this one's pretty tricky. You may want to pause and think about what you can do. Before we've kind of played this game of trying to get the same base. And we know that 2 squared is 4. So we can write that 4 as 2 squared to the power x minus 2 to the power x minus 12 equals 0. And we can trade these places, like this would be 2 to the power 2x. Well, we can make that 2 to the power of x squared, because that would still give you 2x. It's a little bit tricky. You can swap the places of the exponents. So we can make this 2 to the power x squared minus 2 to the power x minus 12 equals 0. So what does this look like? Notice, get kind of a hint in the title. Solving an exponential equation that is in quadratic form. In quadratic form, something squared plus or minus something, that same thing to the first power, plus or minus some constant equal to 0. And we know how to solve those. We can factor them and solve them. So let's do a substitution. That will help us visualize what's going on here. And you may have seen this method before. So I'm going to say let u, just some random placeholder, equal 2 to the power x. And let's replace the 2 to the power x's with a u. This isn't necessary if you can just keep your mind like in quadratic form, but it's a helpful tool for visualizing. So I'm going to play around with the colors here. So this would be u squared minus u to the first power minus 12 equals 0. So hopefully that makes sense. We're replacing the 2 to the x with u, how we define that. Now this looks nice and clean. It looks like something we can factor and solve. So let's just do it with our u's. I would think of factors of negative 12 that would add up to negative 1. Add up to negative 1. Yeah. What would that be? 4 and 3. One of them's positive, one of them's negative. If I want the result to be negative, let's make the 4 positive. No. I want the result to be negative. So let's make the 4 negative and the 3 positive. Negative 4 plus 3 will give us the negative 1. So that means this can be factored into u minus 4 times u plus 3 equal to 0. And if we set these separately equal to 0, I would get that u equals positive 4 and u equals negative 3. But we said that earlier, u equals 2 to the power x. So let's undo that substitution. Yeah, we said that up here. So I'm just going to replace things. Let's replace the u with our 2 to the power x. So 2 to the power x equals 4, and 2 to the power of x equals negative 3. The first one we can see for sure, x equals 2. We get one solution. The second one, 2 to the power x equals negative 3. Is there any value of x that I can plug in that will give me a negative, that will give me a negative 3? Might want to think about it. But let's recall the range of the exponential function. 2 to the power x will look something like this. We can get more specific, but some kind of exponential function that does not exist down there. It doesn't give any outputs that are negative. So this is an erroneous solution. We'll have to throw that one out. So we just get x equals 2. So this one was pretty fun. It's very tricky. If we didn't have that little hint in the title, it might have been difficult to pick out what to do. So keep an eye out for things that are quadratic in form. This applies both here, and we had to do a little bit of manipulation in order to see that quadratic form. So it might even be hidden from plain view. But when in doubt, it's a thing to look out for. And this comes up again in trigonometric equations. This applies, it's a little trick you can pull out of your pocket here and there. Sometimes you're able to pull this off. And it feels pretty good when you recognize it and are able to get it. So keep an eye out. I bet there will be some homework questions that are in quadratic form, maybe in disguise. All right, this was shorter section. We were just practicing solving some complex, or I should say complicated, logarithmic and exponential equations. There was some additional ones using a graphing utility from the textbook, but I wanted to just focus on more analytical methods. All right, that's it for this video, and I'll see you next time.